Okay, good morning, everybody. I'm going to be filling in today for Professor Eager. He's down in Washington, D.C., testifying in front of Congress or something. So just want to follow up from his lecture yesterday. We talked about steel, the steel-making process, and he gave you a kind of rule of thumb that rebar is about 10% when you're pouring steel or having a concrete structure. The rebar, the reinforcing bar in that concrete structure takes about 10% of the volume up. So what we have here is a piece of rebar. This is actually a galvanized type of rebar if you look at the surface finish on it. One of the things with reinforcing bar is sometimes it's numbered by a number. If you're on a construction site, they'll say number 3 rebar, number 5 rebar. Basically, how you'll know what you're dealing with is it just goes by 1/8 of an inch sizes. So number 3 rebar is 3/8 of an inch. Number 5 rebar is 5/8 of an inch. But this is a very important material. If you want to build any concrete structures, you need to have some type of formwork and reinforcing bar in there to make sure that you get those both tensile and compressive strengths. So you can take a look at that, past that. One other thing before we get started, we're going to talk about glass and structural glass applications today. Last week, I wanted to show you guys, we got talking on wire rope and in particular steel wire rope. And I wanted to show you this video. So this was a full-scale test on the about 1.5 inch diameter wire rope. This was performed. If you look at this structure is about 3 stories high, this testing machine that we use to test this. These wire ropes, the strength, tensile strength for this was over 300,000 pounds. So extremely strong, and some of the strength is added by the design, the way they braid the wires. So I want you to, we'll just watch the end of the video where the wire rope fracture occurs. But one of the things, just to listen, if you hear some pings, that's actual pieces, strands of the rope breaking over time. So the way it's designed is that you can break a couple individual strands without the entire assembly of the wire rope breaking. So that was me. I wasn't. It sounded like a bullet going off, or he wasn't really prepared for it when it actually broke. So that was my not smooth camera work there. But somebody had asked about wire rope, so I wanted to show you guys that. But the main thing I'm going to talk about today is, all right, glass manufacturer. There we go. So the main thing for today's lecture, it's going to be glass manufacture. All right. We relatively only recently have developed the manufacturing methods to produce float glass and plate glass, and I'll get into that later. That was around the 1950s when we actually it became more of an industrialized process. But before that, how glass used to be manufactured was, if you guys have ever been down to the basement here in Building 4, we have a glass blowing lab and we have a foundry. And it's really, what we're doing down in the basement there is very similar to how they used to make this glass. They would basically have a man, he would use centrifugal force and twirl the glass, and then you'd blow on it to get different features. But one of the main things was initially, you're really limited by the size glass panel or glass piece you can make. One of the things, if you've ever been to some historical buildings, sometimes you'll see, I guess they call this a bullseye type pattern on the glass. That's indicative of old glass pane that was manufactured by early processes. What you're seeing here is they don't do that like that anymore. You see all the old panels, and then you see this nice, clear, flat panel produced by, flat panel process. So it was really almost like a trade, like a woodworking, something like that. Glass blowing was a trade that they would pass down to apprenticeships, things like that. Here you see an individual actually, blowing the glass and cutting off the edge there of the glass. So newer techniques, now we not only have float glass processes, but we're making glass composites, fiberglass in particular. So the fiberglass process is much different from those traditional processes. What you do with the fiberglass is it gets poured in as a liquid, and then the design of the spinner system here, and these are typically made out of cobalt alloys due to the properties. You have the high temperature properties, issues like that. So you pour the liquid glass in here, and it basically comes out almost like yarn or other type of fiber. And then they can spin it into other types of insulating materials. Fiberglass, we're talking now they're putting in composites on aerospace applications, things like that. So the fiberglass process is very different from those traditional glass processes. But really, one of the main things was the ability to perform a plate glass manufacturing process. All right, so to be able to shape the flat glass. If you looked at some of those initial panes, those early panes made by the traditional glass making processes, the glass was not smooth. They'd have to actually polish it by hand and to get a smooth finish on the glass. So there was, if you look at some of those old buildings, the glass has some type of waviness and curvature to it. It was very non-homogeneous process, and you get variability from one glass pane to the next. So when they were able to come up with the plate glass process, it actually really revolutionized the industry. And what happened was it was produced as a rolling procedure. All right, the starting glass at a temperature where it's softened. All right, plastic condition means the glass was at a temperature where you could work it, similar to how we talked about steels and their annealing temperature, and you get steel at a certain temperature, you can form it. You can do the same with glass. And then they had these two forming rolls, and it would pull off the forming rolls, and they could make it almost a continuous process. They still had some additional work after this to get the smooth surface. So even after this process was performed, there would be a grinding and polishing procedure. So it was much better than the traditional ways, but you still had some manual work to do on the back end. All right, so the float glass process came around. This is an image from Pilkington. All right, this really revolutionized the industry. So the Pilkington, if you guys haven't heard of the name Pilkington, it comes from Sir Alistair Pilkington, and between 1953 and 1957, he and Kenneth Bickerstaff invented the float glass process. This was revolutionary for the industry at the time. It created high volume applications, and you also produced better uniformity with the glass. All right, so what happens in the float glass process is you actually float this over a bath of molten tin. And I have a video to show you in the next couple slides, but you have your molten tin, and it's almost like oil and water, okay? You have your molten glass, raw materials on top. And what happens is when it gets onto the tin, because of surface area and issues like that, it will spread out and it will fill up this whole region here of where your panels end up, coming off the assembly line. All right. Pilkington then licensed this to numerous companies and, became wealthy. And I think then there was some family lawsuits, later on. So, it really revolutionized the industry. One of the things Professor Egan and I discussed the other day was we were talking about, billion tons per year club, and this is a class on structural materials. The float glass in and of itself is about 53 million tons per year produced. So that's on the same range as aluminum alloys. We're still nowhere near steel, right? Steel's like 1.5 billion, whereas this is only 0.05. But this is only float glass. It doesn't take into account glass for recycling and bottles and solar panels and other applications. If you take all glass applications and put them together, we're probably talking about 150 million tons per year. Rather, we're not talking billions, but it's still a significant amount. So this is the float glass process. So after you float it on your tin bath, you still have to strengthen the glass, especially if you're going to put it in some type of application where it's in a building. It has safety curtain wall type application to make sure people don't either fall or are contained within the building. So you have to strengthen the glass, and there's 3 ways you can strengthen the glass. You can temper the glass. All right, you can do a mechanical process, which would be to laminate the glass, or you can do a chemical process, which is an ion exchange, which exchanges the sodium ions, which is the raw material for the glass is basically sand. So sodium, you have other materials. So the ion exchange is used to strengthen the glass by exchanging the small sodium ions for larger ions. And one of the ways they go about that is they can use a potassium chloride bath. So you would be exchanging the sodium ions for potassium ions. And in that way, you can get residual stresses on the surface of the glass, and it's a strengthening process. We're going to be talking about tempered glass later. That's a thermal process. And there's some issues if you don't leave it in the tempering condition long enough. And we'll talk about that when we get into glass fractures. All right, so glass strength. Professor Eager has a story he likes to tell about his thesis advisor, Bob Rose. When he used to teach this class, he would go to a glass manufacturing site in the North Shore here of Boston, and they made light bulbs. And he would go early in the morning and get the light bulb, and right after it's manufactured, the glass, he would be able to bounce it and it wouldn't break. Because right after it's manufactured, you don't have the attack of the air at the surface of the glass. And what really happens is when you have that oxygen on the surface of the glass, it creates these small, micro cracks, micro pits areas over time when the air diffuses, if you don't strengthen it. So that's why in the beginning of the class, he would be able to, bounce the light bulb, but at the end of the class, if he tossed it, it would shatter. Because after, a certain time, you have diffusion and kinetics takes over. And then you lose that ductility of the glass. And one of the Achilles heels of glass is that it's brittle. All right. So, but that's because of over time, the diffusion of oxygen and other things onto the surface. And what you're seeing here is duration of stress, all right, versus ratio of stiffness to density. So over time, you're able to put less stress on it before it breaks. And that's related to the diffusion of the oxygen into it. Thin glass sheet. All right, what you're seeing here, it's a cut off of Corning website for one of their products for cell phones. You can make the glass very thin. All right, this is willow glass. So what differentiates the willow glass from other types of glass, and Professor Eager may talk about this more, is that they were able to invent an alkali-free manufacturing process. So what happens is with your raw materials, you have a lot of alkali materials. And those are the materials that, if you don't do the chemical ion exchange and things, over time, you'll get diffusion in there and you can get the brittleness that occurs. If you use a alkali-free process, that's why you have a little more impact resistance on your glass. We're going to talk about in the last couple slides cell phones and try to tie in how much of a business broken screens on your cell phones are, because it's really astonishing when you look at some of these numbers. But they are, research is going into creating stronger, more impact resistant, glass materials. So before I get into the glass fracture, I want to show you a quick video from the Pilkington website, and this is on the float glass process. So this is just a little, I'm only going to show you about 2 minutes that I think are relevant of this video, but it is on the web. You can watch it if you want to watch the whole thing on your time. So what he's going to start talking about is the raw materials and how they actually float the glass. So this is 60%. Those are your alkali materials, the lime and the dolomite.
Lower the temperature at which sand will melt. But glass itself is also an important ingredient.
That's one of the really important things to note about glass. Professor Eager talked about steel making the other day, the Bessemer process, and how they do what's called hot topping and cut off some of the ingot and reuse it later on. They do the same thing. There's a lot of similarities between steel and glass. In the glass making process, what you were just seeing there, it's called the cullet. That's on when you're in the factory and the glass is floating, through the factory. Some of the panels that are broken or whatever, it drops back down and then it loops back in, and they use that as a starting material for additional glass because it is less energy intensive and it takes less temperature to remelt. So just like they do with steel, with the hot topping and cutting off 30% for reuse in the steel making process, they do the same thing with glass.
And then crushed before being added to the batch. This further accelerates the melting process and reduces the amount of energy required for melting by up to a fifth. All raw materials are rigorously checked to ensure the purity of the batch.
If they don't get all the impurities out, we'll see what happens when we talk about the glass fractures.
Natural gas burned in preheated combustion air then heats the batch up to 2,800 degrees Fahrenheit. Once heated, the batch materials melt and change from a semi-molten state to molten glass. Melting, refining, and homogenizing take place within separate zones of the furnace.
So these plants are half-mile long. They're very, very big plants.
Homogeneous and free of bubbles. Inside the furnace, heat is applied from alternate sides in 15-minute cycles. This assists fuel efficiency.
In the plant, it's very hot because we're dealing with very high temperatures.
This continuous melting process can last as long as 50 hours. The glass leaves the conditioning end of the melting zone at a temperature of 2,000 degrees Fahrenheit through a narrow canal where it passes to the heart of the process, the tin bath. Molten glass enters the tin bath and floats on top of the more dense molten tin, like oil floating on water.
This is what I discussed earlier.
Following the perfect flatness of the tin, so that the upper and lower surfaces of the glass remain absolutely flat and parallel with perfect spectral properties.
So this eliminates the polishing procedure at the end because now you have very smooth glass.
The top rollers controlling the width of the glass are sped up to produce a gentle stretching action. A controlled atmosphere of hydrogen and nitrogen within the bath prevents the tin from oxidizing. When it emerges from the tin bath, the glass is sufficiently hard so as not to be marked by the conveyor rollers.
All right, so by doing the float glass process, you're now able to have a continuous process and you get much more uniformity in terms of the thickness, and you don't have to do the polishing procedure to get nice, properties, aesthetic properties of the glass. So the float process really changed the industry, and now you see, if you've gone to Europe, museums, and they make a lot of very intricate designs from glass material. But if they don't do it properly, you can get glass fracture, okay? So I wanted to pose this question to you guys. What do you think are some reasons for spontaneous glass fracture? All right, and what I want you to see here is I was walking in the other day from the T, and over in building 56, what did I see when I looked up? And I didn't throw a rock at it, but what I saw was some glass panel that had fractured. And the facilities guys were saying, we have another panel that broke. So it's not the first one, and that leads you to some issues, right, in terms of how was the glass made, things like that. But I want to ask you guys, what do you think are some reasons you would get a panel to just break, one day?
Dramatic temperature shift, if you have one side hot, one side.
Exactly. So one of the big issues with glass, especially glass that you put in buildings, is there are multiple panels. It's called an IGU, insulating glass unit. And if you think of it as a sandwich structure, they have a glass bridge in China. They just got a lot of news, past year or so it's been opened. And you can see they have videos of people walking on this bridge thousands of feet in the air, and it's glass, and you can look down. In Chicago, they have the ledge where you're at the top of the Chrysler building, and you can look through the glass. With those types of glasses, they do 3-layer IGU. So what happened was the bridge in China, they had a glass. One of the areas they had fracture, and the reason they had the fracture was because they did not tell the people walking on there you couldn't wear high heels. So one of the ladies had, high heels, and it was a area, and it impacted one of the panels, and it broke one of the layers. But there was news agencies, and the people who made the bridge said, there's no need to worry, we have redundancy. So when they add these other layers, either 2-layer or 3-layer IGU, it's for a redundancy. You can lose one of the layers without somebody falling through or falling out. So they do consider these things in the design. But thermal stress is a very big factor in a lot of the glass breakage. We'll get into some slides that detail why thermal stress and where it happens. But what are some other reasons that you can get glass fracture? Anybody?
Maybe like the outer structure moving around the glass, like the building swaying.
So wind loading, all right, that's an important thing to take into account. They have ASTM, all right, is a big committee, American Society of Testing Materials. They have multiple committees that deal with load resistance and wind loading of glass structures. So wind loading is another very big issue. One of the others is during installation. If there's been some type of impact to the material during installation, that can cause a slight nick that removes the residual compressive stresses on the edge of the glass, and then at some point it can break. If it's not seated inside its encasement properly, so that can lead to failure. And so that would be binding of the glass to the window frame. If it's not put in there properly and there's movement. One other one we'll talk about, it will be if they're in the manufacturing process, if they haven't gotten all of the raw materials that are harmful to the glass to diffuse out. So that can cause what's called nickel sulphide inclusions or lead to spontaneous glass breakage. So this happened last week, and I just walked in this morning and see they're putting new panels in, okay? So this is over building 56 or 66, but you see they're not just, this was the panel that had previously broken, but they're replacing these. So glass fracture can be a very costly issue, and if this was not the first panel to break in this location, it could mean that they might have to replace all of these panels. So it can get very costly. It can lead to court cases, things like that, where everyone's pointing fingers at each other. The glass broke because you manufactured it wrong. The glass broke because you installed it wrong. Things like that. But I just walked in this morning and they're replacing these panels. So we'll see what happens in this case. So as I was talking about IGUs, insulating glass units earlier, okay, here's a patent application. So one of the things I'm trying to show in this patent and this cutaway is here's your two layers, okay? And in between these two layers, you have a gap space. And I touched on this last week when I was giving the material substitution lecture, but one of the issues related to thermal stress is as designers try to minimize this gap space and make the entire thickness of the IGU thinner, as they try to minimize this thickness, what happens is you have less gap space and things are getting hotter in that gap space, and the heat can't diffuse out of the gap space. So you can actually get so hot that it causes a thermal stress breakage in the panels. This is actually more common than you'd think to see glass breaking because of thermal stress. All right, so one of the things I want to show you in the next few slides are actually different examples from different types of glass. We talked about bulletproof glass previously. We talked about float glass and flat panel glass. They actually all have slight nuances that make them different in how they're manufactured, but they can fracture in different ways based on the way they're manufactured. So we're going to talk about a few different failures, case studies, and then we'll talk about what's the proper equipment if you want to do an inspection on this glass. How do you test it? So one of the first things to know is where to look for information, guiding documents, whether they be specifications, documents by technical organizations in the industry. Where do you look to locate how to properly analyze fractured glass? So there's an ASTM standard 1678. It's for the fractographic analysis in ceramics and glasses. And one of the main things is to know the terminology. So very similar if you were dealing with steel, a steel that had fatigued. If you look at glass, the features on a glass fracture surface have similar features to a fatigue fracture surface. They mean different things, but you need to know, the features to look for. So you have the origin, the mirror, the mist, and the hackle are some terms when you're looking at a fracture surface. And what we're seeing here is at the origin. So if you have some singular area where either they did not get out an inclusion, something, a refractory fell in from the glass plant, this is where the defect can start. All right. Normally around this inclusion or defect area, you have a very smooth area, and that's why they call it the mirror. You can almost look at it, it's very smooth. You can see a reflective appearance in there. Surrounding that, and these typically do have this radial type outward appearance, you have this transition area between the mirror and the mist, and then the mist and the hackle. So if you've seen broken glass, you see how the shards branch out in many directions. So the mirror is very smooth and reflective. You have discrete boundary interface areas, all right, the mirror mist boundary, the mist hackle boundary. What we're seeing here is just an example on a piece of glass that had fractured. Additional ASTM standards. All right, you have there is a standard for how to interpret what the fracture surface looks like. All right, you have an ASTM standard on determining the load resistance. So for any type of construction company who's building large skyscrapers, I was just down in Southie at the Seaport area this weekend, and all you see is they're putting high rises up left and right. It really looks a lot different than it looked 10 years ago. But if you're going to be building this type of high-rise structure, you'd have to follow this E1300 standard practice for determining the load resistance. So as somebody mentioned earlier, you have wind loads, You have to take into account all of these things when you're using glass as your curtain wall material. And if you don't, you won't get a certificate of occupancy from the Department of Buildings. So it's really significant. You're dealing with a critical area of your structure. So here's the E1300 practice for determining load resistance, and it's a 80-page document. I was on the committee that put this together for a couple years, and you have different people from different industries. You have glass manufacturers are on the committee. You have end users. You have companies that do the coatings. Because now you have LEED certifications, and you can get a lot of actual tax credits by making a building more energy efficient. So there's a lot of money that can be made when you're designing buildings, when you start to think about using glass and how you're going to use the glass. So we talked about thermal stress. Often with thermal stress, you're going to get the fracture will start on the edge here just because it's under more highly stressed area from two locations. The glass has very decent compressive properties. So if you can stand on the glass like we saw on the previous slide, it doesn't have good properties in tension. So that's why at the edge, if you have both tension and compressive forces, that's where you can actually get your crack to start at the edge. Because one of the issues with glass is it's not good in tension. That's why we put residual compressive stresses in it through the manufacturing process so that it doesn't break. We talked about lighting, sun lighting. There was a famous building in London a couple years ago. The designer who actually designed it has had this issue on 2 or 3 buildings. And the designer was known for his, making conical type buildings. And he had a glass curtain wall facade. And what happened was at one area across the street, 2 blocks down, they were actually getting temperatures so hot it was melting the car hoods and it was like super hot. What was happening was with the building, the design of the building acted like a lens or a mirror, and it focused the sunlight at one spot. So there's a famous picture, if you Google it, it's somewhere in London, and that now the people have known you don't park in that area if you want to leave with the car later that day. That operates. So the sunlight conditions need to really be thought about in the design process, or else you can get these unforeseen consequences once a building's already in service. And the angle at which the sun hits can then affect your thermal stresses. So on some buildings, and there's been case studies, people say, why do I have a building and I have 50 broken panels on this side and no broken panels on the back side? And more often than not, the answer is, well, when the sun comes up and it hits it, you're getting thermal stress breakage if it's in a more regional area. So the thermal stress can actually fracture the glass panel from sunlight. The next type of inclusion I want to talk about is nickel sulfide inclusions. Now, this is typically only found in tempered glass. Okay, so tempered glass, similar to how you can temper steel or anneal the steel, right? Tempered glass is you keep it at a certain temperature that removes any stresses in the glass, and then you can strengthen it afterwards. If you don't leave the glass in the tempered state at either a high enough temperature or for long enough, you can get inclusions that don't diffuse out of the molten glass. And what happens is when the glass solidifies, these inclusions get caught in about the mid-thickness of the glass. So it's important to note for the float glass process, you do have a thickness limitation. Float glass can only make glass about 1/4 to 3/8 of an inch thick. Anything more than that, you have to start looking into using multiple panels and how you're going to arrange. You can't make a 1 inch thick piece of float glass. and it's just because of the physics of this, when you float it on the tin bath, the surface resistance and issues like that. So you have a size limitation. Most of the glass is a 1/4 inch. That would typically be a standard, a 1/4 inch thickness. So if you have an inclusion, it's typically about midway through your thickness. And that's because those are the inclusions that had the farthest to diffuse. And if you haven't left it in long enough, that's where it's going to become trapped. One of the things, if you've seen glass that has a nickel sulfide inclusion, it has this characteristic, they either call it a figure 8 or a butterfly type breakage pattern. And what happens is, the reason the nickel sulfide inclusion, breakage is so scary is because it can happen spontaneously. You can have glass in service for 10 years and it can be fine, and then one day it just breaks. And what's happening is, to cause that spontaneous breakage, it relates to the volume expansion between the phase changes for the nickel sulfide. You have an alpha phase and a beta phase for the nickel sulfide inclusion. When it transforms between those two phases, you have volume change. And what happens is, if it's in the mid thickness, now you're putting tensile stresses into the glass as it expands. So now you have tensile stresses in the glass, and glass doesn't work well under tensile stress. It can accommodate it to some point, but at some stress, it's just going to break. So here's a piece of the glass, and when you're looking at it, actually you don't see much. Nothing really jumps out. So one of the things you have to look at is you have to see what techniques you can use to find the root cause. So if we were going to zoom in on this area here, all right, you see how smooth that is? So we would use, typical equipment used for this would be just a typical stereo microscope to get some higher magnification visual, and then you can use a SEM or EDS to confirm that whatever inclusion is, it has either nickel sulfide. There's other types of inclusions, but EDS will tell you what the chemistry, approximate chemistry of the inclusion is. So when we looked at that glass from a couple slides earlier under the stereo microscope, this is what we're seeing here. So one of the things about nickel sulfide inclusion is it's known to have a more spherical appearance rather than some other types of inclusions that may have a different shape to them. So nickel sulfide inclusion, it's known to have a very spherical shape. And now we're looking at the size scale here, the scale bar here related to the size. So, it's not nanomaterials, but it's also something generally you can't see visually. So what you do is you could put the glass in the scanning electron microscope. All right, so in this case, you have two types of microscopes. Some of the SEMs, you don't need to put any coating, and they can do non-metallics. Some, in this case, there was some gold was sputtered on the surface, so at the SEM, you can actually see what we're looking at. So this is the image in the SEM under higher mag, and you see the spherical appearance, and then we did EDS, and you see you have some peaks for nickel and you have some peaks for sulfur to confirm. Another type of failure in glass is a delamination. Now, this is what you see when you have an automobile. They make the glass a different way. It's called safety glass, okay? And if you've ever seen a car crash, you don't have glass where the windows just break into 1,000 pieces and go everywhere typically. They use safety glass to try to keep it into as many pieces as possible. So how they do that is they actually put a plastic layer in between the two glass layers, and you make a sandwich type structure. That plastic material typically is what's called PVB, polyvinyl butyrol, and we'll get into some slides that show it basically adheres to the glass to keep it from spalling off in many different shards for safety reasons. So glass delamination is what we're seeing here is at the edges, you have multiple layers, and what happens is if the adhesion isn't done properly, one of the layers will start peeling away, and you'll get this frosted or glazed appearance when you have delamination. And over time, it will just get worse, and you have to replace the glass. So one of the main tests they do for safety glass is called the pummel test. And similar to we talked about the Sharpie test for steels, it's not a very exotic test, and it basically consists of taking a hammer and hitting the glass X amount of times, and then looking at visual comparison to see how much the glass adhered or how much glass spalled off. So the pummel test is used to determine adhesion properties between glass and the PVB, polyvinyl butyrol interlayer. This is the criteria. Generally, there's some, the glass manufacturer does this in-house, and they can't really find a ASTM spec for a pummel test. It's not really something that's done before the glass goes out rather than after the fact. But if you want to see, this is after pummel test was performed. All right, so they pounded the glass pretty good, and basically the ratings here is how you would say whether you had well adhered or poorly adhered PVB layer in your glass. So equipment and techniques used when testing this type of glass, you can use all the other techniques we talked about before, but in this case, what's really the issue you're looking at is the adhesion properties between the glass and the PVB. So for that, if you wanted to see if there was any contaminants in the PVB, if there's any issues with the adhesion, to actually test the adhesion properties, you can use some other tests. All right, so Fourier transform, infrared spectroscopy, or you can do dynamic mechanical analysis or DSC. So FTIR, what it does is it measures the frequency and intensity of the vibrations in the molecule. All right. So what it will do is it will shoot a laser through the sample. You can just put the sample, it shoots the laser through, and then what you'll see in the next slide, you get a spectrum, and it compares to a library of hundreds of thousands of different organics, and you can use it to see if there was anything in the PVB layer that could be considered a contaminant. So an example of something would be if you had a caulk, like a silicone type caulk material. When you're putting glass panels together, sometimes you'll caulk the edges, right? But if you get that material on the inner layer in the plant, it can act as a contaminant. So here's just a typical image of a FTIR. Now, this is what would be what's called an ATR equipment. So what happens is you put your sample right there, and you tighten it down, and there's a crystal in here. It shoots the crystal up, and it measures your spectrum over here versus your wave number. So there's libraries. PerkinElmer is a big company. There's hundreds and hundreds of thousands of spectrum for different chemical organics that are out there. And what they typically do is compare it to known spectrum to see, if you have something in there that you shouldn't as a contaminant. All right, so the DMA is a mechanical type of test where you measure the mechanical properties of the inner layer. And what it is basically similar to how you do a fatigue test with a CT, a compact tension specimen, for a metal. You can do this where you vibrate the sample, and it imposes an oscillating strain, and it measures the both elastic and viscous response of the material to that strain. One of the things you can use DMA for is to determine glass transition temperature. That's one of the properties that the glass manufacturer will give a range on and see if it's within that range. So this would be your glass sample in here, and basically you just oscillate it, the test vibrates. It's similar to a fatigue test that you do on a rail sample or something. And then you can do it at different temperatures in an environmental chamber, but then you would measure the mechanical properties of that adhesion. DSC, thermal characterization technique. This is as a function of temperature. So what you do is you put your sample in there and it heats it up, and what you'll see is at different temperatures where you have your phase transitions, it will actually have drops in the resultant curves. So you can do glass transitions, crystallization temperatures, melting temperatures, and you can use this to determine if the glass that you're working with conforms to what the material's cut sheet or technical literature states that it should be. So a lot of times we get involved after the fact, and people want to know, was the glass manufactured properly? Was it installed? Why did the glass break? So it's an iterative process where if there's no smoking gun or something that really jumps out to tell you why the glass broke, you really have to go through this process of doing some additional tests on the glass to try to determine its properties. So what you're seeing here is this is what a DSC type of equipment would be. You have a control sample on one end and your sample under test on the other. And what you can see is either you have a glass transition temperature right here, but these areas where there's peaks and valleys correspond to different functions and phases of the glass. So your recrystallization, your melting areas, and that's what you would compare against the manufacturer's literature. The last one I want to get to is bullet-resistant glass. This was at a site I was at a few years ago, and they wanted to know if there was an issue with the glass because they had a couple areas where there was nicks in the glass and slight areas where the bulletproof glass had indications that something hit it. So they wanted to know what was wrong with their glass. Now, one of the things to note is bullet resistant is not the same as saying the glass is impervious to any type of breakage. All right. Professor Eager showed you the bulletproof glass he had, and it has multiple layers. The one he showed you had about 5 or 6 different layers stacked up. So just because you're buying bulletproof glass doesn't mean that you can't get scratches and breaks in it. So the way they do the bulletproof glass is they have a glass-clad polycarbonate, and that allows the glass to absorb more energy. The requirements for the glass assembly is that the glazing must resist penetration by a projectile, and you don't have any glass fragments flying. So if you did shoot a projectile at the glass and it stopped the bullet and you don't have shards everywhere, that would be a glass that operates as intended. Just because you had a nick on the glass doesn't mean that the glass was manufactured improperly. The last quick thing I want to talk about is cell phones. All right, how many of you guys have cracked your cell phone? I mean, I've definitely done it a few times, right? And then you got to go to the phone company and they get you for $100 or whatever they charge. So the last thing I want to talk about on cell phones, broken cell phone screens have cost Americans $23.5 billion to repair or replace from 2007 to 2014. That's an astronomical amount of money. Everyone wants to be able to watch their movies and stuff on their phone. You have all your cell phones have some type of glass material that you're looking through. One of the trade names you'll see often is Gorilla Glass. I believe that's Corning's trademark. But they've gone through multiple iterations of different types of glass to be used on cell phones to make them more impact resistant, to make them leak resistant. You've probably seen the commercial where the rappers are pouring champagne on the glass and they can still use it. So there's been quite a few advancements in the glass related to the impact resistance for cell phones. I found this little blurb here. More than 25% of all iPhone users have had a cracked screen at some point. New glass designs to increase the impact toughness. So we talked about the Sharpie test, and that's the test of impact toughness. They have a similar test, to try to determine what the impact toughness for glass is. And now I believe they're at Gorilla Glass version 5 or probably the same versions they have of the iPhone they have of the glass. So it's really big business. It's not just architectural. It's not just your soda bottles and other glassware. You know, you have cell phones. You have all these different industries. And if we're talking about structural materials, we're talking about how do we prevent these things from fracturing. And if it does fracture or it does need to be removed from service, what type of equipment do we do to analyze the glass to see, you know, why it broke? So if you guys have any questions, I'll take them now. The one other thing before you turn off the video. All right, the student presentation list was posted. I just looked at it late last night. I think there's an error with the times they put here. So the talks, it's more important to just see what day you're scheduled to go. And the talk should be no more than 10 minutes, 10 slides, 10 minutes. And if you look at the times, we'll probably send out a revised one with the appropriate class time. Okay, so does anyone have any questions? So thank you guys. Take care.